All right, we're starting chapter 10 now, conservation of energy. And as I alluded to in chapter 9, all these problems are going to be the energy initial is equal to energy final. And all our energies are going to go in as positive values. You just got to make sure you put them on the proper side of the equation when you do this. All right, so for example, we're going to take the case of a bowling ball hung by a string from the ceiling. And so the bowling ball will swing in an arc like this. Okay? And down here, when the bowling ball is down here at its lowest point, right here, so that this length L doesn't change, we want to figure out what its velocity is at this point. Okay? So to do that, we're going to do this energy initial equals energy final. So energy initial equals energy final. I want you to start that way every single problem. And I say, what's its initial energy? Well, what gives it all the energy is I'm not going to push it. I'm just going to pull it up and let the thing go. So there's no initial velocity. So the initial velocity is 0. Okay? So the only thing that gives it energy is the height it is right here. Notice the height goes to the center of ball, or what we call the center of mass. And we talked about gravitational potential energy. It's always easiest if you put the gravitational potential energy so that 0 is at the lowest point. Then initially, all it has is gravitational potential, which is mgh. Meaning because it's higher than it is here, it has the energy of gravity, which is going to convert into kinetic energy. And down here, it has no potential energy because we just defined gravitational potential as 0 at this point, but it has a velocity now. And so we're going to have 1/2 mv squared. So all you do is you have to know the height, and you can figure out what the velocity is at this point as it swings through a pendulum. Well, notice if you do this and we solve for the velocity, the masses cancel, so it doesn't matter how massive your bowling ball is. And the 2 goes over here, so we're going to have v squared is equal to 2gh. Or v is equal to the square root of 2gh. Okay? So that's the velocity at the bottom when you started at a height here. But I want you to remember way back from chapter 4 when we had this equation. This equation we use for constant acceleration, or essentially for projectile motion under gravity. Okay, except I'm sorry, this is a minus 2g because gravity is going down. Okay, but look, the initial velocity is 0, so v squared is equal to minus 2g. But what's y minus y naught? Well, y is the final position here. Y naught is the initial position here, so that's a negative value. So this is just equal to negative h. And I get v squared is equal to 2gh because the negatives cancel out. And v is equal to square root of 2gh. Hey, look, those are exactly the same. It has to be the same because energy is conserved. When you start at this height, if you drop the ball straight down, it's going to have this velocity. If it swings, it's going to have this velocity. But you're still starting with the same amount of energy, so you have to end with the same amount of energy. The difference is the velocity at this point is now going this way, and the velocity here was going this way, but the velocity is exactly the same. All right. So when we do these problems, you're going to start them all the same way. You're always going to start with energy initial equals energy final. You're going to plug in the energies. What are the types of energies that we could have? Well, we can have gravitational potential, which is mgh, and we use gravitational potential as g. Capital U means potential, g means gravity. We can have kinetic energy, which is energy of motion, which is just 1/2 mv squared. We can have spring potential energy, which is 1/2 kx squared. And we can have thermal energy, which is friction, which is mu sub K times the normal force times the distance over which the friction occurs. Right now, those are the only energies that we have. So you have to figure out what energies go in which side of this equation. Remember, friction, the thermal energy, always goes on final side. Always, okay? Now, gravitational potential depends. If you start on the top of a hill and you're going downhill, then gravitational potential is on this side. If you start in the valley and you're going uphill, then the gravitational potential would end up on this side. So it depends on the problem where you put the energies. But overall, energy is actually an easier way to solve problems most of the time than doing forces and trying to figure out which way the acceleration is. If we go back to the pendulum here, this would be a difficult problem, almost impossible to solve if we did it the way we did it before. Because gravity is pulling down, but you have a tension force here, so you have to break the tension force into components. But then as it moves, the tension force changes, the components change, so the angle changes. So continuously the forces are changing as you go around. So there's no constant acceleration or constant force. The only way you could do it would be using calculus, because the force or the acceleration is a function of its position along the arc. Much more difficult. But if we do it as energy, boom, it came out really easy. All right, so that's what we're going to do. Make sure you use these types of energy in your equations. All right, there is one more thing we have to do. It is possible if you have work, meaning some kind of external force, then you have to apply work to the equation. So in this case, if it was coming down, the pendulum was swinging, but I was like having wind pushing on it, creating a drag force, that would be put in as work. You would take that force, remember work is equal to the force times the distance times the cosine of the angle. And then whether it's positive or negative, whether the force is in the direction of the travel or against it, would make this positive or negative work. So yes, if you do that case, then the energy initial plus the work external is equal to the energy final. This is the case where you have an external force, only when you have an external force. In all other cases, work is 0, then the initial energy equals the final energy. All right, so do problems 11, 22, 43, 46, 48, and 51. I will do videos of each of these showing you the answers. If you can do all these, then you'll be able to be comfortable and do these on the next test. All right, that is Conservation of Energy, Chapter 10.